At the absolute center of every single atom lies a hyperdense, positively charged cluster of protons and neutrons. Shift to a biological scale, and the same word describes something different: a guarded, double-membrane organelle housing the genetic information of a cell. Despite existing in completely different scientific disciplines, both represent the central point of influence for their respective systems. In physics, manipulating this atomic core grants access to massive quantities of macroscopic energy. In medicine, mapping the magnetic resonance of these very same atomic cores provides high-resolution internal diagnostics. To see how we leverage this scale, we have to examine the mechanics of binding energy, commercial fission reactors, nuclear catastrophe management, and magnetic mapping in MRI technology. Mastering the subatomic realm translates directly into macro-scale electrical power and microscale medical survival. The baseline relationship between central protons and surrounding electrons is known as the effective nuclear charge. To keep those protons from repelling each other, an immense foundational force is required: the nuclear binding energy. The mathematical understanding of this mass-energy equivalence is attributed to Albert Einstein. His formula, E equals mc squared, shows that mass and energy are interchangeable. One way to release that energy is nuclear fusion, the blending of light nuclei. But to overcome electrostatic repulsion, fusion requires temperatures exceeding 100 million degrees Celsius. Sustaining those temperatures on Earth currently takes more energy than the reaction produces, making fusion unfeasible for commercial power today. Instead, we use the opposite mechanism: nuclear fission. Rather than blending light elements, we split heavy ones. The process begins when we bombard a heavy isotope with a slow-moving neutron. The atom fractures into barium-139 and krypton-94, releasing heat and 3 free neutrons. Those 3 strike adjacent uranium atoms, fracturing them and releasing more neutrons, triggering a self-sustaining chain reaction. That rapid exponential cascade effectively converts the subatomic binding energy of the core into a massively concentrated, high-output thermodynamic force we can use. When compared to chemical combustion, the energy density of fission is significant. A single uranium-235 pellet, roughly the size of an eraser, yields the same thermal output as 1 ton of coal. That same pellet equates to 3 barrels of oil, or 17,000 cubic feet of natural gas. A commercial nuclear facility's primary purpose is to capture the intense heat generated by this chain reaction. These facilities use heat transfer systems to move thermal energy away from the core to generate steam, which turns electricity-generating turbines. This energy density makes fission efficient, but the irradiated byproduct of the reaction creates a different scale of environmental risk. Capturing nuclear energy results in the inevitable production of radioactive waste. Low and intermediate level waste consists of items like short-lived radioactive tools, resins, and metal cladding. The most hazardous category is high-level waste, the spent reactor fuel that remains highly radioactive. Isolating this material from the biosphere requires reinforced shielding and permanent geological storage strategies. While it sounds substantial, coal plants actually produce a comparable volume of waste every hour. It is the extreme longevity of the radiological danger that necessitates oversight from bodies like the Atomic Energy Regulatory Board. Harnessing atomic energy successfully replaces immediate, heavy atmospheric pollution, with an incredibly long-term, multi-generational responsibility for the strict physical containment of these elements. When containment protocols are bypassed for destructive purposes, the consequences are severe. The nuclear weaponization of 1945 resulted in massive casualties and acute radiation syndrome across leveled urban centers. Accidents are tracked using the International Nuclear and Radiological Event Scale, or INES. Levels 1 through 3 are considered anomalies. Levels 4 through 6 involve localized consequences and minor human involvement. Level 7 is the highest tier, representing a major, uncontained release of radioactive material. The 1986 Chernobyl disaster was a Level 7 event, leading to reactor core displacement and elevated thyroid cancer rates. The 2011 Fukushima disaster was the second major Level 7 event, illustrating the need for national disaster management authorities. When subatomic containment fundamentally fails, these localized industrial accidents can quickly evolve into devastating multi-generational environmental disasters. Shifting focus from physics back to biology reveals a different way to interact with the atom. In nuclear medicine, radiopharmaceuticals are used as tracers to detect internal anomalies. This field was built on the discovery of nuclear magnetic resonance, where physicists observed how atomic nuclei align in magnetic fields. Modern MRI machines utilize these magnetic fields to read proton alignment, providing detailed internal images without the use of ionizing radiation. Instead of breaking the atom for power, diagnostic medicine reads its natural magnetic resonance to map the human body. Whether it is inside a reactor core or a living cell, the nucleus acts as a concentrated node of potential. Releasing binding energy through fission provides electricity for civilizations, but requires managing hazardous waste. In contrast, medical applications use the same atomic properties for non-destructive diagnostic precision. The risks associated with nuclear systems are a managed trade-off for their high utility and efficiency. The ability to interact with nuclear physics, from generating mass power to mapping cellular structures, shows the current extent of our management over the subatomic world.